Here's one. And there are many, but I'm basically drawing these guys in a T. There are two different versions of this. You can have it pointing down, or you can have the edge of the ring pointing down. But the idea here is, of course, that the negative pi clouds of one are going to interact with the delta positive dipole of the other. Okay, so you have a delta positive sitting right in proximity with that negative dipole. So you have a nice electrostatic interaction, and we call this guy a T-shaped interaction. And technically, what you have here is a CH dipole to a pi pi cloud here. This is technically what you have. And that's one interesting configuration. Now I'm going to show you something, and you can decide for yourself if you like what I'm doing. You can tell me if I'm right or wrong. So imagine this, where these rings are exactly over one another. And I'll survey you, and we'll make this a clicker question. I'll survey you. But do you think this is a good situation? Who thinks it's a good situation? Raise your hand. Look at that, you guys are smarter than me. I drew the wrong thing here. So if it's perfectly stacked, pi-pi interactions in a parallel configuration, perfectly stacked, parallel pi-pi. Let me write it that way instead. This is not too favorable. Okay, so this is favorable. And I'll give it the green check mark here, but this is not too favorable, okay? Okay? It's not good to align the negative pi cloud directly over the other negative pi cloud in this parallel perfectly stacked, like coins, okay? If I had a roll of coins, that's what I'm drawing here. It's always hard to, do this in 3D on 2D paper. But that's what I've drawn. Perfectly stacked parallel pi-pi is not the optimal electrostatic solution for aromatic pi-pi interactions. Instead, what it does, there is a solution on how these quadrupoles like to align with one another, and I'm trying to draw it here, like so. And this is still parallel. It's a parallel pi-pi, but it's offset. Now you might say, well, isn't that still going to not be happy? And I'll tell you that actually this situation here is actually quite happy, and it's as good of an interaction, it's as favorable of an interaction as you get in the T-stack, okay? So remember, you got your positive in there in your quadrupole, and you have your negative charges here, your negative partial charges in the loops. And so when you do it like so, you just get enough beneficial interaction here between the various negative and positive charge groups. You get enough attraction, you get your nice van der Waals contacts, that this is the way that aromatic rings like to stack, a little bit offset, and not perfectly stacked, if they're going to be parallel to one another. And of course, this is what's happening in Kevlar. So I already told you the hydrogen bonds are going to give you these beautiful sheets, and then the offset aromatic parallel stacks are going to give you this three-dimensionality to the fiber and give you this beautiful set of interactions in the other plane. Okay? So that's why this thing is tough as nails, literally, or samurai swords, which I get to say at least 3 times in this lecture. And then I'll stop. All right, so now, once you start to make your polymers, and you put them in, I think, extremely hot sulfuric acid. It's kind of a nasty process. I don't know if they've improved on it yet. And then they push it through a really fine hole, and eventually they realize that you put a little air gap between it and some solution, and you basically what you're doing is spinning fibers. And so these polymers are actually coming together and building these interactions on the fly, and then being extruded down into some solution to catch them, and you're making Kevlar fiber. Then you can weave that and do whatever you need to do to make vests and all kinds of other things. But let's just try to zoom in on a fiber. So here's the end of a fiber, which is under extreme magnification. And I'm going to try to make a pie cutout here. I made the same joke in the other class. So this is the end of a fiber. For people that don't like my drawings, this is an end of Kevlar fiber here. And I've cut it away so you can imagine that these benzene rings and their bonds are parallel on this axis. Okay, so these polymer chains are doing hydrogen bonds in these planes. And then as you go around the wedge, it's not clear exactly how it resolves in the middle. But these sheets of aromatic rings in this hydrogen bonding array, these sheets, are going to actually then stack on one another and be glued together by aromatic interactions between the sheets. So you'll have aromatic pi-pi, we'll say offset, parallel pi-pi for each of those, between those wedges of pi, and then in that thing. And then the sheet itself is built out of hydrogen bonds. So the sheets are stacking in this way. And you might say, well, if they're individual sheets, then this fiber would just be brittle and just break, right? Because the chains are finite lengths. Well, that's true, but down the sheet axis, it's going to be quite a bit more complicated. And when I'm drawing it like as a separate sheet, it's really not. It's really quite infinite. And if you were to look at these fibers, and these are aromatic rings, sometimes let's say a fiber would terminate in the middle of a sheet, then another fiber would just pick up right underneath it. Okay? And then say a neighboring fiber would actually be contiguous next to it. So it would effectively glue any defects that you would find together in these polymer sheets. And so you'd have offset and staggered polymer chains throughout, gluing together these sheets. These sheets are made of just, because of the beautiful structure of this, these hydrogen bonding interactions. And so then basically, you'll have your sheets in this guy, and then the sheets will then stack on one another with these aromatic, these pi-pi stacking interactions. So that is why this is incredibly strong stuff. And I guess we have a little bit of time, but does anybody have any idea, based on the structure of the Kevlar chains, how what I've drawn here, we'll do a zoom in, and how you might imagine, how would this resolve itself here? So the question is how would ends potentially interact? How might you expect the ends of two Kevlar chains, how would you expect the ends of two Kevlar chains to potentially interact? Does anybody have any idea, based on the chemical structure? hydrogen bond, but even stronger than a hydrogen bond, what else might happen at the ends? You remember what you have? You have an amine and an acid. And what is an acid? What kind of charge might an acid take on at neutral pH? Negative. And what does an amine take on it? So you get both hydrogen bonding and electrostatic. It's going to be a nice way to basically bridge these chains, individual chains together. Even though it's not covalent linkage between individual chains, you have a strong ionic bridge, hydrogen bonding interaction there, sealing these chains together. And so you're going to have a strong. The answer, maybe this is a question here. Yeah, and the answer is there's going to be strong ionic hydrogen bonds. And so for people it's a good review. That's why I'm doing this. So at neutral pH, this is a situation that you'll have. This guy will tend to want to be protonated. Now, and you can imagine a neighboring guy here, and he likes to ionize, as we've drawn in the past. Now, it might not always beautifully work out like this, but this is going to be the low energy configuration, so we can at least academically imagine it's happening. I mean, I don't know if this is real. But what you have there is you have the ability of having a positive and a negative charge in proximity and this hydrogen bond. So, so you have a hydrogen bond here, and then you have an ion pair. We haven't talked about them, and I mean to lecture on it a little bit. But you have an ion pair, a plus and a minus charge, which are very attractive as well. So this is one way, potentially, at the ends could bond and make Kevlar yet stronger. At least I just thinking about it here. Okay, any questions about Kevlar? Okay. Oh, and that was my reminder to do that, but we're not going to do that because we just did. And I wanted to, before we do a clicker question, I wanted to talk briefly about a biological polymer that's made of polyamides that actually occurs in the neurodegenerative diseases like Alzheimer's disease, and it occurs in other tissues in the body, but it's particularly devastating for those folks that get this disease. And basically what happens is a protein is secreted outside of neurons. And in extracellular medium, this protein accumulates, but it actually begins to assemble, much like Kevlar individual polymer chains, that these individual protein chains assemble into these long, impossibly tough fibrils called amyloid fibers. And these amyloid fibers, I'm not going to write down a lot of notes. I mean, this is the kind of stuff that's just for fun, and we don't put on the exam, but to maybe spur curiosity in health sciences too. And but the idea is that basically these long fibers form. And they look kind of like this. If you looked at them under this electron microscopy, and they're like thin bars that slowly twist, over distance, and you see these twists and these long ribbons. And this is incredibly tough on your body and your brain. Okay, and it's hard to clean up this material. It's very insoluble. It's very tough, almost like a biological Kevlar in some sense. I doubt spider silk would be the closest to that. But basically, then it's held together. It's held together with tons of hydrogen bonds between these proteins that stack in a beta sheet configuration. And beta sheet's very similar to Kevlar, where all the monomers are in extended 180 configurations, much like a para-substituted Kevlar. And it builds these giant structures. It's quite incredibly tough. And so again, proteins being polyamides can make amazing fibers too, which actually can be quite life-threatening. I don't know of any sort of I don't know of any positive implications of amyloid formation yet. Although whether it's the causative, or the effect of having Alzheimer's disease is up for debate. Many people think they're smaller fragments of this assembly process that are much more toxic. In any sense, that's where I wanted to end. Again, proteins are polyamides. Proteins have this structure here. And these R groups here represent different functional groups for different amino acids. But in any case, there's a repeating unit of a polymer, a protein polymer, and here's that amide bond. Here's that amide bond that forms between adjacent amino acids. So that is in essence used to build the structures of proteins. And this particular amyloid configuration is built up with tons and tons of beta. We call them beta sheet hydrogen bonds. Those bonds are stacked like this in these layers of sheets. Build up. And the real structure looks like it's a trimer kind of configuration, looks like kind of like this. But in any case, that's a general idea. So I wanted to end with a clicker that should be, actually it seems like the last class some people missed it, so hopefully we'll do better this time. Let me turn it on, get your clickers going, and give everyone a chance here to. Am I going to do what? I don't know, maybe. Okay, guys, already people seem to know the answer. I'm impressed. Okay, so which intermolecular force interaction stabilizes Kevlar? And there's one on there that I hadn't even talked about, but it's called the cation-pi interaction. It's a very important interaction where just a cation can sit over that pi cloud. It's quite stable, but you can decide for yourself whether you think that occurs in Kevlar or not. I need to put 4 choices. I just felt like adding something else. So talk amongst yourselves and give it a shot. Okay, let's check to see. People are still clicking in. Sorry. Oh, I'll put it back up. I just had to check. There's lots of clicking going on. Anyone have any questions? Anyone have any complaints? Fruit to throw at me? I'm very agile. Oh. All right, so hopefully people have finished up here, and I'll give you the answer. Okay, it looks like we settled down. There's only 424 of you today. And the answer is that B There are no T's. Okay, so Kevlar, remember Kevlar arranges hydrogen bonds to make parallel sheets. And the sheets don't want to do this. That would be kind of funny, right? They actually want to line up with one another in an offset parallel. They don't want to be aligned perfectly. That gives you electrostatic repulsion between the pi clouds. And the cation-pi interaction does not occur. And so we can look at the graph. There were some of you that bought into A and bought into C. And at least somebody picked E every time. All right. Have fun in lab.